Dear friends, in this video, we will cover the concept of Bayes' theorem with an application example. The famous mathematician Bayes developed what's called an inverse probability rule, which updates the previously calculated probability based on additional information available. It was developed in the 18th century. It is an extension of conditional probability. It has got very powerful message for decision making. Let's look at an example. A drilling company has estimated a 40% chance of striking oil for their new well. A detailed test has been scheduled for more information. Historically, 60% of successful wells have had detailed tests, and 20% of unsuccessful wells have had detailed tests. Given that a well has been scheduled for a detailed test, what is the probability that the well will be successful? Let's understand this with certain symbols. Supposing striking oil is considered successful, let S represent successful, S bar represent unsuccessful, meaning no oil found. D represents detailed test. D bar represents no detailed test. We are given certain facts which are at the start of the exercise. Probability of S, that means success rate is 40%. So probability of S is 40% or 0.4. And therefore, probability of S bar is 0.6. We are also told 60% of the successful wells, given the fact that there are 60% of the successful wells which had undergone detailed test, and therefore probability of D given S is equal to 60%. Similarly, 20% of the unsuccessful wells have had detailed test, and therefore probability of D given S bar is equal to 20% or 0.2. These are called prior probabilities. We have clearly been told at the very start of the problem. They are available to us. Now we have to revise them using this information to answer the question, what is the probability given that a well has been scheduled for detailed test? In other words, we want probability of S given D, which is called the posterior probability or the revised probability. What we are given is very interesting to see. Probability of D given S, which is important, which is not useful to us in the sense how good the test is, the detailed test is, if we are able to improve the success rate by performing the detailed test. In other words, the inverse probability, ulta, probability of D given S is there, but we want probability of S given D, which tells us a story whether the detailed test is effective or not. So we want to calculate the probability of S given D, which will tell us whether the detailed test is effective, which means this probability must be more than the prior probability already available of the strike rate of 0.4, and that is given to us already. Similarly, D given S is 0.6. So let us see whether this improves by performing the detailed test, whether the probability of success improves. Let's look at this. Let's formulate the association of attribute table as before, which you can see here. Attribute D, D bar on the rows, the detailed test, attributes S bar on the columns, the fact whether it is successful or not. And total, let us convert the whole thing into 100 wells to avoid the fraction for better clarity. Out of 100 wells, 40 wells are successful, 60 wells are unsuccessful. Now, let us plug in these numbers. We are told the probability of D given S is 60%. In other words, 60% of the successful wells, 40, which means this is 24 wells, which is the joint event occurrence of both detailed test and success. In other words, 60% of the successful wells have had a detailed test, and therefore 60% of 40%, 40 wells, we will get 24 wells as DS. Similarly, 20% of 60 is 12, which gives the joint occurrence of D and S bar. This gives the joint occurrence of D and S. The total is 36, which you can do. And therefore, out of 100, 36 wells had detailed test. So 64 wells had no detailed test. Now this is D bar, which is 16, which is saying out of the 40 wells, 16 wells did not go through detailed test. And this is 48, a simple subtraction addition. We have completed the table. Now what we want to answer is probability of S given D. Given there are 36 wells which underwent detailed test, there are 24 that are successful, and therefore this is equal to 24 divided by 36, which is equal to 2/3, which is equal to 0.67 to 2 decimal places. And therefore what we are saying is, given D, which is 36, what is the probability of success, the conditional posterior probability, which is 24 by 36, simplification gives us 0.67. We notice now this 0.67 is better than the original prior probability of 40%, and therefore it's prudent to consider at the prima facie level, go ahead with the detailed test. Subject, of course, cost details. I have not given that, but certainly Bayes' theorem has given the insight. It is worthwhile exploring doing detailed test because the strike rate improves to 0.67 compared to the prior level of 0.4. Therefore, it is worth doing that. In other words, the strike rate is 40% initially. Now, posterior analysis using the Bayes' theorem says it's approximately 67%. Therefore, it's worth doing a detailed test. And that is the beauty of Bayes' theorem. And we have been given D given S, but we are calculating S given D, which is the wonderful insight that is provided by Bayes' theorem. I hope you have enjoyed the video. Thank you very much. We will see you in the next video.